All right. So we're back. This is the last lecture before we're going to start reviewing everything. Did anybody have any questions about the homework? Any questions? Yeah.
How do you tell if a system is leading or lagging?
If the phase is negative, that means that it's lagging. If the phase is positive, that means that it's leading. Okay? But if you're looking at it graphically, here, let's look at it graphically. I do this every time. So the one that was here, the signal that's leading is the one that occurs earlier in time. So the peak of the red signal occurs earlier in time than the peak of the blue signal, which means that that signal's leading. The blue signal's lagging. All right? Any other questions? There was a lot of questions in my office, so I'm assuming the rest of you who didn't come figured it out. One thing I wanted to cover, because a lot of people asked about it. So basically the tan inverse function, if I plot it up, it looks like this, okay? And so when you do the phase, right, you're using the tan inverse of the imaginary over the real, okay? So when I have an inductor, it's purely imaginary. There's no real part. So I'm going to be plugging in some imaginary, positive imaginary number divided by 0, which is like positive infinity, basically. And you note that this is an asymptote. Like, it doesn't keep going up. It asymptotes at this value. Well, this value is pi over 2. And in degrees, that's 90 degrees. So that's why when you plug in some positive value over 0, basically for an inductor, you'll always get a phase of 90 degrees. For a capacitor, you're plugging in a negative value, so you get negative infinity, and this is negative pi over 2. So that gives you negative 90 degrees. And when you do a resistor, you plug in 0 over something because there's no imaginary part, right? The imaginary part is 0. So if you're trying to find the phasor representation of an inductor, you're going to get 90 degrees every time for the phase. For a capacitor, you're going to get negative 90 degrees every time. And for a resistor, you're going to get 0 every time. But when you start adding these, like resistors and capacitors or inductors and capacitors, then that's when you get phases that are between negative 90 and 90. Because now you have a piece from the capacitor that's causing some shift this way, and then a piece from the inductor that causes a shift this way, and what you get is some resulting phase shift. But if it's just a pure capacitor, it's always going to be negative 90, pure inductor always positive 90, and resistor will always be 0. Okay? Question?
So you said it will always be the imaginary number over the real number when you're doing this with a resistor and capacitor or inductor?
Yeah, I mean the formula is, let me go over here. That's the formula for phasor, right? And that's assuming that my number is in the form x plus jy, right? So this is my imaginary number. And so my real is on the bottom and my imaginary is on the top. And so with a resistor, I basically have R, nothing else. It's just R. The impedance of a resistor is just R. So that's the equivalent of R plus J0, right? It's just R. And so when I plug that in, my phase is the tan inverse. My phase is the tan inverse of my imaginary 0 over whatever. But when I get tan inverse of 0, it's just 0. So my phase angle for a resistor will always be 0, right? Now for a capacitor, it's 1 over j omega c, right? Which is the same as minus j times 1 over omega c, which has no real part. It's 0 minus this. My real part is 0. So if I go to find the phase, I basically get whatever the imaginary part is, y over 0. But it's going to be negative because of this negative here.
Right.
And so it's basically tan inverse of negative infinity, which gives me minus 90. All right? And then for the inductor, it's j omega L, which gives me, it's basically 0 plus j omega L, right? My x is 0. So then I get phi equals the tan inverse of a positive value over 0, which evaluates to 90 degrees. Okay? Makes sense?
Yeah, but none of those would have been on the homework, right?
None of those would have been on the what?
On the homework.
Yeah, they would have.
They would.
When you're trying to find V out.
Yeah, no, but I'm saying like the example. If you're trying to find V out, you do one of those.
Yeah. Yeah, so when we had those circuits on the homework, we had a source, we had a resistor, and then we had, whether it be a capacitor or an inductor, it's just an impedance. And so to find V out, it's I times basically whatever this impedance is, Z, right? And so if that impedance is a capacitance, it's going to have a phase of negative 90. It doesn't matter what size capacitor it is. If it's a inductor, it's going to have a phase of 90. It doesn't matter what size inductor it is, because all that matters is that there's no real component to that piece. But for the total, right, the total, now you have R plus, right, this R plus whatever, I don't know, let's say it was the inductor, it'd be plus j omega L. Now you have a real part and you have an imaginary part, so you get a phase that's not 90 or negative 90 or 0. It's somewhere in between, because you have a real component and an imaginary component. So you basically plug this in and you get omega L over R, and that's going to give you some value. But if the real part's 0, then you're going to get infinity here, and if the imaginary part's 0, then you're going to get 0 here. But for the total, right, that's not going to be the case. Any other questions? Any questions about anything I said here? Okay, so I've got a couple options. I can talk about more AC stuff. I can do more examples.
More examples, we're gonna have design.
Yeah. Let me do a harder one. I'll do a harder one, and then and then it'll lead me into another topic, and I'll talk about it briefly because it's part of 221 also. So let's do we're gonna do an RLC circuit. It's basically gonna have all three, and it's no different. Again, it's basically like you might as well treat it like 3 resistors, because it doesn't matter. They're all just impedances. Is everybody okay with that? They're all just impedances. They don't. The inductor and the capacitor in the context of RL and RC circuits, you have to think about all this crazy stuff. In this context, you don't. You just have to treat them like another component that impedes the flow of electrons. And you have different equations, of course, that you have to remember. So let's just do an RLC circuit example. Let me throw something in Spice first so that I don't pick something ridiculous. Yeah, I just want to make sure that I don't get like something where the output is 0 or something just absurd, because it can happen if the frequencies aren't right. I'm going to do something that's going to seem kind of magic, but I'll also just talk over it. It's not something you'll need to know, but I want you to see it, because it's also going to be a part of 221. So let's just make this 10K. Let's make this let's make it 10 microhenries. Whoops. And we'll make this like 2 nanofarads. And then what I'm going to do something called AC analysis, okay? This is something we haven't seen before, but I'm just going to do it for the reason of determining whether these are reasonable values. So what a AC analysis does is it sweeps this circuit over every frequency within a range that I give it, and it basically looks at what is the ratio of my output to my input over all of those frequencies. Okay, so I can pick at that point a frequency where I'm like, okay, I want to operate here because I want my output to be 1/2 of my input or something. So I'll show you. You'll see what I mean. It's probably sounding ridiculous right now, but you basically give it an AC amplitude, which I'm just going to give it 1. It's 1 volt basically. It's saying I have a sine wave of 1 volt magnitude, and I'm not setting the frequency. Instead, I'm going to sweep the frequency. And I'm going to look at what is that ratio between V out and V in. So if V out is basically 0.7 volts and V in is 1, I'm going to get a ratio of 0.7. And it's going to show me that ratio for the entire spectrum of frequencies. Okay? This is a very common thing. It's called frequency response. Let me write that so that we have it. This is just, I'm just brushing over this. I don't expect you to know it. Okay? So when I do a frequency response, I hit run, and I get this thing here called AC analysis. This is going to be useful for you. The type of sweep you want to do is decade sweep. What a decade is it's a factor of 10. Okay? So I'm going to go basically from, let's say, 10 hertz up to 10 megahertz. Like, I'm going to sweep this huge frequency range. And that would be impossible in any other context. Like, I can't go from 10 to 10 million on any reasonable plot. So what it will do is, instead of evenly spacing units, like 10 to 11 to 12, it will evenly space decades. So it'll go 10, 100, 1,000, 10,000. So each unit will be a factor of 10 increase. This is very common in frequency response. You'll see this all the time. So all you really have to know is that a decade is multiplying by 10. Okay, each decade is a factor of 10 jump in frequency. Okay, number of points per decade is just me telling Spice how many points I want it to plot. So we usually do 100. You could do less, you could do more. If you do less, it's going to look zigzaggy. If you do more, it'll be really smooth. Hundreds, like kind of optimal. And then a start frequency and a stop. So I'm going to go from 10 up to 10 meg. And I'll run it. And then I'll show you what it looks like. So V in is constant. V in's not changing. It's going to stay at, let me change this to linear. I don't want to get into decibels. Okay, so it's 1 volt for all frequencies, because my input is not dependent on the frequency, right? My input's not changing based on the frequency. My output is going to change based on the frequency. My input is not. And so what I get is I get this plot right here. And so this is telling me that for this particular circuit, I'm looking, so this is going to be something that nobody's really used to seeing, okay? You're seeing frequency on the x-axis, right? My variable here is frequency. That's the only thing that's changing. So basically what this says is that 10 hertz, right? My output is basically equal to my input. You see that my output is 1 for all of these times, okay? And then, or not time, sorry. See, that's the problem. See, it's so easy to think in terms of time. It's not time, it's frequency. There's no time here. These are different frequencies. All the way out to some point where the output starts dropping, right? It starts dropping. And that means that, so basically at 10 kilohertz, right, you can see this frequency, I can plot it right here. Let me drop it. Right on 10K, my magnitude of my output is 624 millivolts. Okay, so that's literally telling me if I were to run this circuit right now in a transient at a frequency of 10K, my output voltage would be 624 millivolts in magnitude. And then the dotted line is my phase. Okay, so this is basically a way of looking at how an AC circuit behaves instead of at one frequency over all of the frequencies, because this is really important. When we use these AC circuits, we use them for filters. Basically, a filter is a circuit that will allow certain frequencies to pass through it and not allow other frequencies to pass through it. And so this circuit right here would allow all of these frequencies to pass through the output, because basically my input and my output are the same. That's a filter. It lets those through. But way out here at these high frequencies, it doesn't allow the signal through. It's basically, it's doing what's called attenuating. It's basically knocking the amplitude way down. So this is why this is important. But the only reason I did this was so I could pick a frequency and show you that that's going to be what I'm expecting. So let's try and get it to exactly 10K. Okay, so we're expecting a magnitude of 622 millivolts on the output. Okay, does everybody see that? And a phase of negative 51.5. So let me just write that down, and then we'll solve the circuit, and that's exactly what we should see in the transient. Any questions about this? Yeah.
This is not related to this, but I was thinking about this before you started.
why do we like call impedance like, since it's resistance anyways, why don't we just call it resistance? What's the significance of calling it impedance in AC circuits?
Literally just because impedance, what impedance is it is
Something that
it is the well, it's got two parts. It has a resistance and a reactance. I don't know if you saw my group message about that. Some people might have. Basically, when I'm looking at, let me go back to my page here. When I'm looking at, so that this is what we're going to expect to get out of this circuit. But when I'm looking at a circuit, or sorry, an impedance, it has two components, right? I write it as X plus JY usually, but if I write it as R plus JZ or something, I don't know, this part would be my resistance, and this part would be my reactance. The reactance is the frequency-dependent part of the impedance, and the resistance is the non-frequency-dependent part of the impedance. We can think of it as a resistance because that's the way that it behaves, but to say that it's a resistance would say that this isn't a resistance. Like you can't use resistance to make up a resistance, so they decided to call the resistance plus the reactance the impedance.
yeah.
And reactance is just the term for that imaginary part of the impedance, okay? All right, so now that we've got that, this may or may not have been confusing. I'm sure it was slightly confusing, but all you really need to know is that I'm looking at this circuit and I'm sweeping the frequency that I'm putting in and checking what the output's going to be based on all these different frequencies, okay? So just for an example, let me throw a dot tran here for, I don't know, let's do 100 milliseconds or something. And I'm going to run at 100 hertz, okay? At 100 hertz, my output and my input should basically have the same magnitude. That's what this is saying. So let me go ahead and put a sign here now. I'll go 0, 1 volt, and it's a ratio, right? So if my input was 10, the ratio is going to hold true. So then it would be, if my ratio was 0.7, my output would be 7 volts, right? It's a ratio to the input. We just put 1 to make it easier to look at. But if I were to put AC 10 down here for an amplitude of 10, all of these would shift up. It's just a ratio, right? Yeah, what's up?
What's the red dotted line?
It's the phase.
Oh, okay.
So the dark line is the magnitude and the dotted line is the phase, because we care about magnitude and phase, right? So this is the magnitude changes as the frequency changes, as well as the phase changes as the frequency changes, and this is showing you. So on this side you can't see it because I shifted it, but over here we have degrees, right? This is phase.
Okay.
Yeah.
Wait, you're taking what's the phase?
The dotted line.
Dotted.
The dotted line is the phase. So right here it says phase, right? If I right click on that axis it says phase. And you can do don't plot phase if you want, and then you'll just get magnitudes. But I don't know how to undo that. Whatever, it doesn't matter. But okay, so basically I'm going to throw 100 hertz in here, and we're going to see that my output should be roughly equal to my input. So let me go create a sine wave. 0, we'll do 1 volt like I said, and we'll do 100 hertz, and then Nothing Else Matters by Metallica. So there's my input and there's my output. They're exactly the same. You see that? So when I ran the AC simulation, that's exactly what it told me would happen at that frequency. Right? Does that make sense? Okay. So now, at the frequency that we're concerned with, I said 10K. I said it should be 622 millivolts, right? So let's go 10K and see what happens. Oh boy. It's because I ran for way too long. Alright, so I said 622 millivolts, so let's zoom in and see what this magnitude is. 620.2 millivolts, basically, right? So that's what the point of the AC plot is so you can see what's my output going to be at this frequency, without having to run a million transient simulations. Because all the transient simulation does is show you these pretty sine waves, but if you know what it's doing, you don't need to look at this. You can just go look at the AC plot. And that's what you're going to do. There's an entire segment of 221. The whole chapter 14 is frequency response. And all it is how does this circuit respond to different frequencies? It's literally all that I just showed you. But then they get into this annoying part where instead of using volts over here, they use decibels. Nobody really understands why they use decibels other than Baker. So if he's around, ask him why they use decibels, because I can't answer. I don't know why they use decibels. I always switch it to linear because it makes more sense. No, it's I couldn't answer it. I don't know. Like I'm not even going to try to answer.
Frequency of sound decibels, or is it something else?
It's something else. It's a unit. It's used to make the frequency phase plot look linear, but I don't know how it does that. It does something that instead of making it look loopy, it makes it linear, and I couldn't tell you how. But it makes it's another thing that makes the hand calculation and analysis of this stuff easier to do it by hand, because then you can just draw a straight line and a straight line. It makes the hand calcs easier. But looking at it in Spice, I almost always just tell people to switch this to linear because the decibels just don't make sense. I don't know what they are. 0 dB is 1 volt, or a ratio of 1. But like I said, I'm not going to get into that. I just wanted to show you that this worked. So everyone should at least see that this worked at the frequency I said it was. I got the magnitude I said I would. Okay, so now let's go back to my paper. Well, let me draw the circuit. So I've got sine wave, resistor, an inductor, a capacitor. This is 2 nano, 10 micro. Oh, you guys, some of you need to really do a better job with these micros. I almost think you're doing it to make me not know whether you were trying to say micro or milli, so that it could be ambiguous, so that you could say, I was doing micro. Like, there's a huge difference between the micro and the milli, like a factor of 1,000. That's a big deal. Micro is usually drawn like this. Milli is an M. Like, those are two very different symbols.
I just make mine look like a weird U/P.
It should be distinguishable. Like, it should be, this is clearly not an M. Like, if you saw this, you'd be like, that doesn't look like an M. That looks weird. That's an M. Like, but some people just draw them like this all the time in any circumstance, and I'm just like, I got to give them the benefit of the doubt, but I don't want to. On the final, please make it obvious. Or I'll just do everything in nano and pico.
That'd be great.
And then you don't have to distinguish.
That'd be worse.
All right, so here we are. The first thing we always I don't know what size to make this input. Let's just do 1 volt since I already did that. Okay, so 1 angle 0. Let me be consistent. If I make that 1 angle 0, then over here I have to, and if I want it to be a cosine wave, I have to come over here and make it a phase of 90, right? All right, and then I'll say that my frequency is 10 kilohertz. All right, let's go back to the paper. So I'm going to go ahead and convert this into a phasor circuit, or I guess basically just impedances. That's an impedance, that's an impedance, that's an impedance. All right. This is 1 angle 0. This is 10K. So my inductor, right, it's J omega L, so it's going to be J times 2 pi times 10K times 10 microhenries, right? Everybody cool with that? So I'm just going to go straight into the calculator with that. 10 times 10 to the minus 6. That's 10 micro. Then I have to multiply by 2 pi and by 10 kilohertz. So I get 0.628. Okay? And now my capacitor is 1 over j omega c, right? So here, let me just write them here. right? So now for my capacitor, I'm taking 2 pi times 10k times 2 times 10 to the minus 9, and then I'm inverting that, 1 over that. So I get 7.957 K.
What's negative J?
Exactly. Again, when I do 1 over J omega C, I basically end up with 7.957 K over J, and then my 1 over J is equal to minus J, so I write it like this. Right? Okay. So, let's go ahead and, whoops. What you'll notice is that inductor could basically be neglected, right? If I'm going to add all these, in terms of the current at least, if I'm going to add all these, that inductor may as well not be there, because I'm going to have a minus J 7.957 K, and I'm going to add this little baby decimal value to it. But I'm going to do it anyways. I mean, you realize this is 7,957. I'm not even writing the decimal point, and this is just a decimal. So like, this is why the values are weird when you pick them randomly. That's why I did the AC plot. So if I'm going to add these together to get my total impedance, I would basically go Z total is 10K plus J 0.628. Did I do something wrong? Maybe let me just make sure I did that right. Somebody else confirm. 2 pi times 10,000 times 10 times. No, it's just because the inductor is so small. If I did 10 millihenry, it would have been more relevant. If I did 10 henries, it would have been way more relevant. Basically, it's just going to be irrelevant in terms of the impedance of the capacitor at this particular frequency. Okay, so then I do minus J 7.957 K. That's my total impedance, right? And so all I'm saying is, if I take this and add it to this, I'm going to basically get the same value here. Yeah?
How do you get the 7.957?
That's from 1 over J omega C.
And C would be
2.
2 times 10 to the negative 9.
Yep. Yep. All right. So that's my total. So let me group like terms. Basically, this is the part where I'm saying that it's going to become irrelevant. It's basically just going to be, we'll just say 0.795. Here, let me do it in my calculator so you can see. Yeah, it's 0.7596 basically. So I basically have this, right, minus this little decimal. It's just going to stay, so it's not even going to change. That's my total. That's in rectangular, so we're going to, if we want to actually do anything with this, we're going to have to convert it into a phasor, right? So if I want to convert this into a phasor, I'm going to go the magnitude of Z is equal to the square root of 10K squared plus 7.957K squared. Do that. Oops, I did something wrong. Anybody else doing it with me get 12.779K?
Yeah.
Okay. And now I need to find the phase. So I go phase is equal to tan inverse of basically negative 7.957 K over 10K. And what you'll realize is that this is a capacitive circuit, basically. This is a capacitive circuit is what we'd call it, because I'm going to end up with a phase shift that's negative. If I end up with a phase shift that's positive for the impedance, that would be an inductive circuit. And if I end up with a zero phase shift, that would be purely resistive. Okay? So even though it has an inductor and a capacitor, we had noticed right from the beginning the capacitor was dominant. So this is a capacitive circuit. Depends on the frequency. It also depends on the size of these values. In this particular case, it's capacitive. Okay, so Let's go with the tan inverse of negative 7.957 over 10. Realize it's a ratio, so you don't need the k's, right? The k's cancel. Negative 38.5. Anybody get that?
Yes.
All right, so this is a phi of negative 38.5 degrees. Therefore, my z total could be described by 12.779 k angle minus 38.5 degrees. All right? Ohms, right? Okay, any questions about that? Now I'm going to find the current. It's the same process, right? It's going to be voltage divided by the total impedance. Right? I equals V over R. So let me switch colors. So I is going to be equal to V in divided by Z total, or 1 angle 0 divided by this thing. I'm just going to round that 7.9 to an 8. What's my phase going to be? It'll be positive 38.5, right? Because I'm doing 0 minus negative 38.5. So 1 divided by 12.79. I get 78, nope, sorry, 0.78 micro. Nope, 78 micro. 78.2 micro. Anybody get that? Let's go check. Spice. Someone had a problem with this. Does everybody notice the arrow's pointing the wrong way here? If you don't flip that, you will get the wrong values. But again, you don't have to take the current there. You can take the current from either of the ones that are actually pointing the right way. Okay? I got 78.2 micro. It's going up to about 80 micro. Everybody see that? This is my current. Where the heck is it? There it is. So I get 78 micro. Everybody see that? Hold on. Good? All right, and then the phase, I'm not going to take the time to do it, but you just take the time delay and all that good stuff. All right, so that we got. Now we need to find V out. Let me label this node too, and we'll find this one too, because I think that'll be helpful for everybody. We'll call this like VX. All right, let's go back to the paper. So we've got I, we've got Z total. Now we need to find V out. Okay, so I'm going to need another piece of paper. Here, you know what? Let me write this. And then let's write these values. Draw it over here. Okay. All right, and then again this, I don't feel like doing it again, so this is minus J times 7.957 K. And again, that's all we're going to need to find V out, right? Because if I just take I times that impedance, that gives me the drop Let me switch colors. That'll give me the drop across this impedance, and this is V out right here, right? Just like in DC, what you could do is you could find this total impedance, and you could go V in minus V out over that impedance gives you I, but that's just not worth it, right? But when we do Vx, we're going to have to do something else. What we're going to do is we're going to add these two impedances, and what we're going to see is that V out and Vx are almost identical because that inductor was so small that it doesn't matter. So just so you can see that in SPICE, before I even calculate it, let me show you. We get V in, we get V out, and then we get Vx. You see how Vx and V out are almost identical? That inductor is so small that it's not contributing anything. It's basically a wire. It's at a frequency for that particular size where it's acting like a wire. Okay, so we can do the calcs and it'll prove to be the case. But let's go back here. All right, so we want to find V out. V out is basically equal to I times the impedance of the capacitor, Ohm's law. The impedance of the capacitor is minus J 7.957K, and I have in terms of a phasor, which is 78.2 angle 38.5 microamps. And so what I need to do is I need to get a phasor for ZC so I can multiply them, right? And so again, this is where it comes in, right? This is a capacitor. Immediately you should know, not you shouldn't have, I mean now you should, that this has a phase of minus 90. You're gonna learn to just know that, and you're not even gonna have to calculate it anymore, because what you're doing is tan inverse of a negative imaginary over 0, which is that plot we just showed. It's negative infinity, and it goes to basically negative pi over 2, which is negative 90 degrees. So I could show it, but I mean tan inverse of negative 7.957K over 0, it's gonna give me minus 90. All right. If you want to try and plug it into your calculator, I was showing people this earlier. What you would do is tan inverse of negative 7.957K, divide by some really small value, because you're just basically taking some huge negative number, and you get negative 90. You see that? And then just to show you that it's pi over 2, if I go put my calculator in radians, pi over 2 is equal to this. If I now go tan inverse, let me just delete this. If I go tan inverse of this thing, I'm going to get that value, right? That's negative pi over 2, right? See that? All right, so let me go back to degrees. All right, so I got negative 90 for my phase. Now I need to find my magnitude. My magnitude will always just be this value if there's no real and imaginary part, because what I'm doing is, phi. What I'm doing for my magnitude is I'm doing the square root of the real part squared plus the imaginary part squared. Well, the real part's 0. So all I'm doing is a square root of the square of this, which is itself, right? So it's basically 0 squared plus 7.957K squared. Well, clearly square root of square goes away, so that's just 7.957K. Therefore, ZC is 7.957K angle minus 90 ohms. Right? Now I've got ZC in phasor, I've got I in phasor, I just multiply them, that gives me my V out, alright? I said it was like 622 millivolts, so we should expect that this times that gives me 622 millivolts. So it's basically 78.2 times 10 to the minus 6 times 7,957, 622 milli, 0.622, right? So that is basically, for phasors, right, I multiply the magnitudes, I add the phases when I'm multiplying. So it's going to be 0.622 angle negative 90 plus 38.5 is going to be negative 51.5. Is that right? And that's volts. Any questions about that? Nothing? All right, so does everyone realize if I wanted to find this value here, Vx now, all I would do is I would incorporate this, what was it, J 0.628. Now I would add these two, right? And I'd get a total impedance here, and I'd multiply I by that total impedance, right? Yeah.
This is 0.622.
Okay, so let me write it. So V out is I times ZC, which is, it's going to be a lot here. I'll just write it down here. 78.2 micro, angle 38.5 degrees, times 7.957 K, angle minus 90. It's multiplying this times this. The magnitudes multiplied gives me 0.622, and then the phases added gives me negative 51.5. All right? And then, yeah, I'm not going to do the one for Vx, but if I wanted to, I would just take minus J 7.957K, add this 0.628 to it. I'd get a new value. It's basically the same. That's why the output looks exactly the same in SPICE, because that impedance, that effective impedance is almost exactly the same as just this impedance. That's negligible in comparison. Okay? Yeah.
You could also just find equivalent impedances in voltage divider if you wanted to, right?
You could.
Okay.
You could. So if we wanted to find V out in a voltage divider here, we could take this piece, and voltage divider it. Or we could take this piece and that piece and voltage divider it. But since this inductor is really just negligible, if we just did the resistor and the capacitor, we'd get basically this exact same thing. All right? Okay, so we already did it in SPICE. Let's go back to the AC, because I think that'll be interesting. Because I want to show you that the phase at 10K should be negative 51.5. And you can do the same thing with the current. If you plot the current in the frequency response, it'll do the same thing. It'll give you a plot with the magnitude and phase of the current. Let me uncomment this. Run. What the heck? Oh, well, that's dumb. LT Spice just erases the dot and puts a semicolon there. You're supposed to put a semicolon in front of the dot. This is why I told you not to look at decibels. Linear. So my phase, let's go to 10K. Is that dotted line? So 10K, there's my phase, negative 51.5. See that? And then my output is 622 millivolts, which is exactly what we calculated. So these will be really useful. This is chapter 14 of 221, basically, is understanding these plots and what you're looking at and learning to understand how this plot's going to look based on the components you have. It's kind of annoying, but it's not all that challenging. If you understand what you're looking at, it makes it a whole hell of a lot easier. If you don't understand what you're looking at, it's just a bunch of lines, and then you're just going to be confused. Yeah, what's up?
So, I don't want to I'm going to think about what I was trying to ask. Sorry.
All right. Any other questions? Yeah.
So resonance frequency is when the impedance of the, like in an RLC circuit, it's when the impedance of the inductor and the capacitor are at their lowest, right?
It's not when they're at their lowest. It's when they cancel each other.
Okay.
So yeah, that's what I was going to talk about next. Just briefly, if we have what's called resonance, a resonance frequency in these circuits, okay, where there's an inductor and a capacitor. And that is the frequency at which this minus J and this plus J cancel each other out completely. So when we add them in series, all we get is the R. Okay? So there is a frequency that exists in every RLC circuit called the resonance frequency between the capacitor and the inductor. And that is the point at which basically capacitors and inductors like cycle charges into and out of one another, and there's like this sort of loop of energy happening. And there's one frequency in each RLC circuit that exists. I'm on the wrong thing, I guess. There's one frequency in each of these circuits that exist where this minus J times something and this plus J times something completely cancel each other out, and that imaginary component, the reactance, is gone. That's the resonance frequency. And so what you end up with is an RLC circuit, but at a particular frequency, you could just solve everything from the resistor, because the capacitor and the inductor aren't even playing a role in the circuit. They're almost like occupying each other. Like the capacitor is distracting the inductor from doing anything, and the inductor is distracting the capacitor from doing anything, and the only one doing anything is the resistor. That's kind of some way that you could think about it. That's not actually what's happening. What's that?
It's like a group project.
It is like a group project. Resonance between two idiots that don't contribute, and you doing everything. Don't be the idiot that doesn't contribute.
Be the resistor in life.
Be the resistor in resonance. Ay. Okay, yeah. Did I answer your question?
Yeah. So then, when you have a higher like capacitive impedance, it's a capacitive circuit then, and then if you have a higher inductive impedance, it's an inductive circuit.
Right, and the reason for that is that you're going to end up with a phase shift that's negative
Right.
when it's a higher capacitive impedance, which makes it a capacitive circuit, and you're going to end up with a positive phase shift when it's an inductive circuit. And then at the point where they're resonant, they cancel, and you just get zero phase shift.
So in SPICE, that would be where the red line meets the red dotted line, right?
It would be where the red line is at zero. Oh, sorry. No. It might be. I don't know. Is it? I don't think that they have anything to do with each other.
Okay.
Because if I shifted this up, these are two completely different plots.
Gotcha.
I think it's where the dotted line is zero, which is basically way up here somewhere.
Okay.
And that's probably because of the way I selected these values. Let me select it. Because the way that an RLC circuit's frequency response is supposed to look is not like this. This looks like a capacitor's frequency response. And the reason being that I picked the inductor so small. If I make the inductor significantly bigger, we're going to get this like bell-shaped looking thing. And then the peak of that is probably going to be the resonance frequency. So let me see what happens if I do this. I might have to mess with these values for a minute.
What about
10 henries is unreasonable, so I don't want to do that. Maybe it has something to do with this.
1 Henry?
Let me see if changing the capacitor does anything. Ugh. What if I do micro here? Yeah, the bell's over here now. Okay. We're getting somewhere. I might have gone way too large.
So it's basically half a bell curve?
No, it should be a full bell curve. I'm just an idiot, and nothing's working.
Dude, if you're an idiot, I don't know what I am.
Stop. Where's the bell? There's supposed to be a bell. It might be. It's because the resistor's too big. Nope. Sorry, guys. I don't teach 221. There it is. All right, it was because it was too big. Okay, we're getting something weird here. This is called an LC spike. So the output goes above the input at this point. I don't see the phase being zero. All right, well, there's the bell. I don't know why the phase isn't zero. It should be, because if the capacitor and the inductor cancel each other, then you get a phase of zero. Mathematically, that's what would happen.
Right.
Maybe something weird's happening in the sim.
I think I got it.
All right, yeah. All right. What do we got? 25 minutes? Anybody have any other questions about this?
Actually, I do have one last question.
You have another question?
So the phase that we're measuring is the phase between the input voltage and the output voltage, right?
Yeah, or whatever. The input voltage and whatever we're looking at.
But in this specific case, it is the input and output voltages?
Yeah, and if it was the current, it's the current and the output voltage and the input voltage. Like, it's not the input current. Well, I guess that you could think of it as the input current.
Right.
But the input current and the input voltage are in phase because they're both the same source,
The
right?
reason I was asking that specifically is because I know for capacitive circuits you have voltage leading, or is it the other way around?
For capacitive circuits, the voltage should lag.
Right, yeah, it's voltage lagging current, and then the other way around for inductors.
Exactly. So let's go back to the transient. It's not going to look very inductive here.
Right.
It's almost basically purely capacitive. So let me comment. So what we should see is that the current should lead the voltage, like you said. And so we get input, output, current. And so my output voltage lags my current. And so that's you can know it's a capacitor just based on that, a capacitive circuit based on that. And it would be vice versa for the inductor. So for your homework, you should have gotten that one of them, the current lagged the output, and the other one, the current led the output, because one of them was capacitive and one of them was inductive. Question?
So when you're working with a capacitive or inductive current, is the difference between the phase difference between the output and the current always going to be a difference of 60 degrees, 90 degrees? Sorry.
Hold on. Let me see if so wait, you're saying if you have a capacitive circuit, like if it's
Capacitive or inductive, it's going to be the phase shift between those two would be 90 degrees. If I'm misunderstanding or not.
So hold on. So let me just say what I think will answer your question, and if it doesn't, then we can reword it. If I have a capacitive circuit with no impedance, which will or no inductance, no inductance, there could be how many resistors you want, however many capacitors you want. As long as there's no inductance, the phase shift will be minus 90.
Yeah.
If you have an inductive circuit and there's no capacitance, the phase shift will be plus 90. And if you have a resistive circuit with no inductance and no impedance, then the phase shift will be 0. But if you mix these components, then you get somewhere between minus 90 and 90 for your phase shift.
Yes, I get that, but I'll ask later.
Well, you can ask. I mean, I
think
clearly
about
am
it.
missing
Trying to
something.
word it properly.
Well, the thing is, if you were to plug this in on an oscilloscope and do it in the lab, you would see this. Like if you put an RC circuit in there, an AC signal into an RC circuit, you're going to get a 90-degree phase shift that you can actually physically see on the oscilloscope. And a 90-degree phase shift would be a 1/4 of the cycle time delay. Whatever the cycle time is, or the period. Cycle time and period are used interchangeably. Whatever 1/4 of that is, that will be your phase shift. If it's inductive, it'll be one way. If it's capacitive, it'll be the other way. And if it's resistive, there will be no phase shift. You'll get the same. Another thing, though, that's difficult is current on an oscilloscope. You need a very special type of probe to measure it, because they use what's called a current probe. I mean, that's kind of self-explanatory. But what it does is it clamps. So if this is the wire, it'll clamp around the wire, and what it's doing is it's measuring the magnetic field around the wire and converting it into a current. Because magnetic field and current are related in inductive circuits. So if you take the current or the magnetic field around the wire, you can very easily convert it to current. And those probes are like $10,000. Like, they're ridiculously expensive. So like a really accurate current probe is expensive. So when you're in the lab, you're probably only going to ever be looking at voltages. You're not going to be measuring current in AC circuits. But you could calculate the current if you know the impedance and all that good stuff.
What I was saying was the phase, when you calculate like the phase shift, and you're like V out is equal to this voltage and then this phase shift,
Mm-hmm.
and then the current phase, the current phase shift, will the difference between the current phase shift and the voltage phase shift always be 90, or can it change? Because in this case, the difference between the two of them is 90.
The reason it worked out that way is because the inductor was contributing so little.
Right. Okay.
It won't always work out that way.
Okay, but if the inductor if it's more of an inductor, it will be between 0 and 90.
Right.
Okay, that makes sense.
And
That's what I was curious about.
Yeah, and on the homework, you might have seen the same pattern, that they were 90 degrees apart, but that's because there was a purely capacitive circuit and a purely inductive circuit. There was no mixture of capacitors and inductors.
Yeah, but when it's in a purely capacitive or purely inductive,
It would be
then
ni-
it would be 90.
Yeah.
So that's a way that you can check your work if it is a purely conductive or a purely capacitive.
Yeah, exactly. Because what you're doing is you're dividing the current by that value, so
Right.
you get a difference. And when you divide phasors, you're subtracting or adding, so it always adds or subtracts to 90.
Yeah, okay, cool. Yeah, that was my question.
All right, any other questions? Yes.
What are your last few comments or statements about life, philosophy that you want to impart?
We still have a whole other week.
Really? You should write a book on it, James.
On what?
On life, philosophy, how to win at life, how to be James Bond.
You guys are crazy. Next week, I'll give lasting comments that you can take with you into the rest of your life.
Sure.
Spicy PBL.
No.
Yes, just like spicy